Hi guys, hope you all have been doing well. So today we are going to continue some more review. Again, this is important just because all year we've been doing solving equations. And every unit we've had a different function and we've learned to solve it. But it can be a little bit easier to solve an equation within a specific unit because you know what type of equation you're going to have. Now in the future, you're just going to have equations. It's just going to be part of the solving process, part of the steps of calculus, part of the steps of other classes. And you just need to be able to recognize how to solve it no matter what type it is. So that's what your practice problems today are going to focus on. So today, like I said, the video is really going to be mostly review. Now, I would recommend if you want to fast forward through a lot of this, you're welcome to, especially if you remember it. But I would at least watch the last few minutes because some of those examples are a little bit different than some things we've seen in class. So the last 3 examples in your notes, I would at least fast forward this to the last few minutes to watch those. All right, so we're just really going to go in order for how we learned those this year. So we started with absolute value. So remember, with absolute value, we had to set up 2 equations. The reason for that is because the absolute value of -2 is 2, but the absolute value of 2 is also 2. So if I just have the absolute value of x equals 2, I get 2 possible answers. Now, there's 2 different ways that you could show this work. But again, the first step, regardless of how you do that, is to get the absolute value by itself. So first thing I would do is I would subtract 1, divide by 2, and then I need to write 2 equations at this point. Now there's actually 2 different ways that you can do this. I can do x minus 7 equals 5 and x minus 7 equals -5 and solve both of those equations. What I also could do is x minus 7 equals 5 and negative x plus 7 equals 5. Either of those are going to work. They're still going to get me to the same place. It's just a matter of which one you're more comfortable with. I'm going to do x minus 7 equals -5 just because that's just more of my habit. Then go ahead and solve both of these for x. And you get 2 possible answers. Now, you'll see in the very top in big capital letters, for every equation that you do, you need to check for extraneous solutions. In almost every type of problem we had so far this year, you had the potential to get extraneous solutions. So always go back and double check and make sure those answers actually work. If I plug in 12, okay, that does work. If I plug in 2, that also does work. So I get 2 answers. All right, looking at our next one. Absolute value is already by itself, so we'll go ahead and set up 2 equations. 2x plus 18 equals 2 plus x. My second equation, 2x plus 18 equals -2 minus x. We'll go ahead and solve that first one. I get x equals -17. -16. Go ahead and solve our second one. I get 3x equals a -20, so x equals a -20/3. Now, when I plug this back in, all right, let's say I plug in -16 here. I could go ahead and plug in -16 there as well, but I really don't need to, because at this point what I have is the absolute value of 2x plus 18 is equal to a -14. And one thing we know about absolute value is that it has to equal a positive number. Absolute value is not going to equal a negative, which means that answer is extraneous. Well, let's look at the next one. X equals -20/3. Same problem. 2 plus -20/3 is going to be a negative number. Absolute value is not going to equal a negative number. So this is extraneous as well. Which means this graph, or this function, or equation, wow, this equation has no solution. All right, so let's move on. So after absolute value, we did quadratics. All right, so with quadratics, you had a lot of different methods for solving. Completing the square is one of them. Completing the square we actually used more often for rearranging and rewriting into vertex form. And that's really an important application of completing the square. That'll come back whenever we did conics, if you remember, and when we're trying to find inverses. You also can use completing the square to solve. Completing the square is my favorite method when A is 1 and B is even. I think it's a really fast way and a little bit faster than quadratic formula. So the way we can solve by completing the square, I'm going to go ahead and move that -1 to the other side. To find the value that I add to complete the square, take b, divide it by 2, and square it. If I add 4 to the left of the equation, I add 4 to the right of the equation. Now remember, if it's on the same side, I would subtract it. But again, it's on the opposite side of the equal sign, which is why I'm doing the same one. So this becomes x minus 2 squared equals 5. So x minus 2 is going to equal plus or minus the square root of 5. So x is going to equal 2 plus or minus root 5. So when a is 1 and b is even, I think completing the square is a lot faster than quadratic formula, because you don't have to worry about all those simplifying steps. All right, but sometimes completing the square, you just might like, or quadratic formula, you just might like better. So we have to know quadratic formula. It's your no-fail method for solving quadratics. So x equals negative b plus or minus the square root of b squared minus 4ac all over 2a. So again, quadratic formula does always work, but again, it could be slower. So we'll go ahead and do this. So negative 2 plus or minus the square root of b squared minus 4ac all over 2a. So negative 2 plus or minus the square root of 4 minus 24, which is negative 20. Remember, negative numbers under a square root become I. Root 20 simplifies to 2 root 5, so this would be 2I root 5. And again, in order to simplify with quadratics, I cannot just cancel out just those 2's. I need to be able to divide both of those by the same thing as the denominator. In this case, I can, so I get negative 1 plus or minus I root 5. Then the last method for quadratics is probably the most important, because you need this method for things other than solving quadratics, and that is factoring. Factoring is your fastest method, and you're going to use it for other purposes as well. So make sure you are comfortable factoring. So start by setting it equal to 0. There are a lot of different factoring methods. Again, you can split the middle, do your AC, so find what multiplies to 36, adds to negative 12, split your middle, do your grouping. That works totally fine. You also can do these a little bit faster sometimes. So one thing you can do is go ahead and make your parentheses. You know those first two numbers have to multiply to 4x. So they could either be 4x and x or 2x and 2x. You know those last numbers have to multiply to 9. So they're either 1 and 9 or 3 and 3. Then your middles have to add to a negative 12. So then it's really just messing with your signs and kind of just doing different combinations of these numbers in order to kind of get those middles to work out. And that can be a faster way if you don't have a lot of possible combinations or if you're dealing with some prime numbers. Now, in this particular case, there's actually an even faster way to solve this, because you may recognize this is a perfect square trinomial, which means it's 2 factors into 2x minus 3 squared. So your only answer here is 3 over 2. But again, factoring is really, really important and going to come up a lot in a lot of your future math classes. All right, after factoring, we went to polynomials. Again, a reason factoring is important is because it can save you a lot of time. All right, let's look at this first one. Check to see if you can factor by grouping. And in this case, I can factor by grouping, which makes it really easy to find my possible solutions. So, well, it's not completely factored at this point. So let's keep going. 4x squared minus 9 is a difference of squares. So you get 3 possible answers. X equals 3 over 2, x equals negative 3 over 2, and x equals 2. Now with polynomials that we can't factor by grouping, it's a little bit of a longer process. So you may have remembered these. These are the ones that took a while. It's not that it's hard, but it did take a while. This is when we use that P over Q and the synthetic division. So again, this one does not factor, at least using grouping. So what we do is we come up with our possible rational zeros. Factors of 6 divided by factors of 1. So all those possibilities are plus or minus 1, 2, 3, and 6. So then what we do is we test them using synthetic division. And it really kind of is just a guessing process. I'm going to go ahead and start with 2. just because I think that one does work if I remember correctly. Synthetic division, bring down the first number, multiply, add down the column, and I get 0 as a remainder. Remember, 0 as a remainder shows you that 2 is a 0. So one of my answers is x equals 2. Then I look at the remaining polynomial. If it's quadratic, great. You can go ahead and find your other two answers. If it's not quadratic, you got to go through that process again or see if you can factor. In this case, it's quadratic. It does factor. So we can see our other two answers are x equals 3 and x equals -1. All right, from there we went on to rational functions. So with rational functions, you really had two different methods you could use. Really depends on what you preferred. One option was cross multiplying. So this worked best when you had a fraction equal to a fraction. So in this case, I can multiply this diagonal. So after we cross multiplied, then from here, we can distribute. And I end up with x equals 6. Again, we still need to check for extraneous solutions. In this case, we're good. So then our other method that we talked about for rational equations was to solve by getting a common denominator. So in order to get that common denominator, we'd factor. So we can see that left fraction is missing the x plus 3. The right fraction is missing the x plus 2. And once the denominators were the same, in order to solve, all we had to solve was the numerators. Because if the denominators were the same, when you add and subtract fractions, you don't change the denominator. So in order for them to be equivalent, we just need the numerators to be the same. So here I would have x squared plus 3x plus 2 is equal to 5x plus 10. Since it's quadratic, I need to set it equal to 0. And then I can factor. And again, check for extraneous solutions. -2 is an extraneous solution because if I were to plug it back in, that would give me 0 in the denominator. And we can't divide by 0, so -2 is extraneous. X equals 4 is our only solution. All right, then we moved on to radical and root equations. So this first one with those rational exponents, I would get that x by itself. So I would add 14. Divide by 2. And then at this point, I can raise both sides to the 4/3 power. So then I end up with x equals 27 to the 4/3. Now keep in mind, 4/3 is an exponent, means the cube root and then raised to the 4th power. So the cube root of 27 is 3. 3 to the 4th power is 81. All right, if we had more than one radical, we can still square both sides. But remember, when you square the side with the plus, remember, you are not squaring the individual components. You have to remember that is the square root of x plus 3 times the square root of x plus 3. And we actually need to FOIL that out. Since it is a perfect square, it ends up also with that square double square trick. So we square, we double, and we square. At this point, though, we still have a square root. So now we need to get this square root by itself. And then I can go ahead and divide by 6, or I can square it at this point, whichever part you want to do. Just remember that 6 is going to get squared as well. But I'll go ahead and get it by itself because that's what we're used to. All right, let's square both sides. Then at this point, it's quadratic. So I can factor out an x. So I end up with two possible solutions, x equals 0, and then I have 1 over 36x equals 1. So x is equal to 36. So again, check for extraneous solutions. Let's make sure these both actually work. And in this case, both of these solutions do. But remember, it is possible to get extraneous solutions on these radical equations as well. All right, after radicals, then we went to exponential and log equations. And that's what we've been doing kind of in this little online time. So exponential equations, you really have two different ways you can solve them. If you need to get an exact answer, if it's possible to rewrite the bases in terms of the same number, that's your best way to get your exact answer. So in this case, I can, because both 7 and root 7 can be rewritten with the same base. Now keep in mind, we are not changing the equation. I cannot just square root this side, because if you just square root one side, it changes your equation. You have to do the same thing to both sides. What I can do instead is rewrite the square root of 7 as 7 to the 1/2 power. So then at this point, the bases are the same, and then I can just go ahead and just solve the exponent. So this would be x plus 2. Now in this case, though, a little bit weird. Okay, if I subtract x to the other side, then I would have -2 equals 2, which we know is not true. So this actually has no solution. All right, that's the method that we would use, but that's not actually going to be a correct answer to this one just because of the way it's set up. It's not possible for these two things to ever be the same. All right, now sometimes it's not possible to rewrite these in terms of the same base, or sometimes there's just one base that has an exponent. So if that's the case, we're going to need to use logs. So on this one here, we'll go ahead and get the exponent base by itself. So I would subtract 7, and then I would divide by 2. And then at this point, I can rewrite this as a log. So remember, the base of the exponent is the base of the log. So this would be log base e, but we don't write log base e. We write ln because it's natural log. So this would be natural log of 7 over 2 equals x minus 2. At that point, your last step would be to add 2. And that would be your exact answer. Now, you can, if you have a calculator at this point, plug it in. But again, we don't want to solve with a calculator until we get this point so that we have the most exact non-rounded answer possible. Right, then we had log equations. So for log equations, there were two different types. We either had log equal to log, and we can just set the arguments equal, or we had to rewrite in exponential form. Regardless of the style that you had, one method we wanted to always do was to condense our logs using our properties. So on this one, I want to condense those two logs on the left. So I can do that. If the logs are added, I can multiply the arguments. So that becomes 8x minus 28. Set those arguments equal to each other. So that leaves me with 7x equals 30 and x equals 30 over 7. Again, just make sure you don't have any extraneous solutions. In this case, we're good. All right, and number 2, again, set the argument, or we can't set the arguments equal, but we can condense those two logs on the left side. So that would become log base 2. X plus 1 times x minus 1 is a difference of squares. So that's x squared minus 1. And since it's not a log equal to a log, it's a log equal to a number, I want to rewrite it in exponential form. So in exponential form, that would be 2 to the third equals x squared minus 1. Add 1 to both sides, square root, and we technically would get plus or minus 3 here, but keep in mind, -3 would be an extraneous solution, because if I plug -3 back into the original, that would give me a negative argument. So my only answer here is x equals 3. All right, so this last part is the new part. Well, it's not new. You've seen a couple that are like this, but really this is going to go a little bit more than what you've seen in class. And these are kind of what we like to call factoring in disguise questions. So looking at this, it may look a little messy, all right? But this is actually a really easy question if you rewrite it and you're able to see that it's actually factorable. So what I mean by that, let me go ahead and set it equal to 0 first. So what I'm going to do is I'm going to replace the 1 over x plus 1. And the reason I want to do that is because that 1 over x plus 1 is squared, and that 1 over x plus 1 is to the first power, which is really similar to our quadratic questions. So I'm going to plug in a variable. You can plug in any variable. This year, whenever we've done these, we've used u just because you'll see it in future classes. And I like to use a variable that's not x so we don't get confused and think that's what we're solving for. So this would be 6u squared minus u minus 1 equals 0. Well, then we can see that's a pretty easy factoring question to factor. So I know my last two numbers are going to have to be 1s because they have to multiply to 1. My first two numbers have to multiply to 6, so either 1 and 6 or 2 and 3. I'm going to use 2 and 3 because, again, I'm going to need my middles to be -1. Well, since I want them to be negative, I need this one to be minus and this one to be plus. So now that it's factored, I can figure out that u is equal to 1/2 and u is equal to -1/3. Now again, keep in mind, we're not solving for u, we're solving for x. So at this point, I need to go back, take what u was, and plug it back in. So 1 over x plus 1 is equal to 1/2, and 1 over x plus 1 is equal to a -1/3. So then I can just solve what's a pretty easy equation now. Over here, I'm going to get a -x minus 1 equals 3. So I'm going to get that x is equal to -4. All right, the last two questions are pretty similar. Again, some of them are a little easier to see, some of them are a little bit harder to see. But I'm going to start by setting this equal to 0. So 2x to the 1/3 minus 3x to the 1/6 plus 1 equals 0. So what I'm going to use for my u in this problem is I'm going to let u equal x to the 1/6. Because if I have x to the 1/6 squared, that's x to the 2/6, which is x to the 1/3. So that makes this 2u squared minus 3u plus 1. And again, this is now a pretty easy factoring question. All right, I know these have to be 2 and 1. This has to be 1 and 1. They need to multiply to, or the middles need to add to a -3. So this is minus and minus. So u is equal to 1/2 and u is equal to 1. Again, we're not solving for u, we're solving for x. So x to the 1/6 is equal to 1/2, and x to the 1/6 is equal to 1. Raise both sides to the 6th power, so that's going to be 1 over to the 6th. So that's going to be 1 over 64. Raise this side of the 6th power, and that's just going to still be 1. Again, same idea on the last one, it's just figuring out what we need to plug in for our u. In this case, I'm going to let u equal the square root of x, because the square root of x squared is just x. That gives me u squared minus 13u plus 36. Again, we can factor this. So this is going to factor into u minus 9 and u minus 4. That does not look like a 4. So u is 9 and u is 4. Again, we're not solving for u, we're solving for x. Plug it back in. So square both sides. So x is 81 and x is 16. All right, so that's it for your solving review. Again, you've got some practice problems, you'll work for a completion grade, and you've got your 7A check. If you need any help, you can do the video request. You can do the Thursday Zoom session. If you need the Zoom session on Tuesday or Friday, you can. Just need to email me ahead of time. And then, just again, feel free to send me an email if you have any questions.